Having learned the characteristics of forces and the various types of forces, let's now apply these concepts to solve everyday life situations. Before we deep dive into solving dynamics questions, let's do a quick revision. We have learned in Module 1 that when forces are balanced, the object is in equilibrium. The net force, that is the resultant force, is zero and Newton's first law applies. So, if the object is at rest, it will remain at rest. And if the object is in motion, it will continue its motion in a straight line at constant speed. If the forces are not balanced, there is a resultant force. This is a situation where Newton's second law of motion applies, and the resultant force and acceleration can be computed using the formula F equals to ma. We also learn the various types of forces. What you must remember is the direction of each of these forces. With this knowledge, you are ready to learn how to solve examination questions. For dynamics, there are 5 types of commonly asked examination questions. In this lesson, we will cover the first 2 types of the questions. Type 1 questions aim to test a student's ability in identifying the forces acting on an object. So let's practice that. We have here a car going up the slope. A common question asked in examination would be to identify the forces acting on the car and the direction of each force. Let's approach it systematically. As we have learned in Module 2, one force that exists on all objects is its weight, which is the gravitational force exerted by the Earth on the car. This force acts downward towards the center of the Earth. The second type of forces that act on the car are the contact forces on each of its wheels that is touching the floor. Contact forces have to be perpendicular to the surface producing the contact forces. Note, if you combine these 2 contact forces into one, then you must call it the resultant contact forces acting on the car's wheels. The third type of forces are the resistive forces, which can be a combination of the frictional forces acting on the wheels as well as the drag or air resistance as the car moves forward. At this point, let me highlight that not all cars are designed to have all its wheels driven by its engine. Some cars have only its front wheels driven by the engine and its back wheels are free rolling and not driven. Towards the end of this video, I will explain why the direction of friction on these wheels driven by the engine can be forward pointing. For now, let's combine all the resistive forces of the object and treat the body as a point of article, where all forces act through the same point. So the total resistive force should always be against its motion. Now, what if you have the car going down the slope? Then the difference is that the total resistive force now is acting upwards because resistive force always opposes motion. And the contact forces will still have to be perpendicular to the floor. Same concept applies for a car on a level ground. The resistive force will always be opposing its motion, the contact forces will always be perpendicular, and there will always be a weight pointing downwards. If you have understood this, you have mastered this topic, because even if I give you a diagram of a man skiing, you will be able to identify the forces acting on him. That is his weight, the contact force, and the resistive forces. Next, we look at a case where tension forces are involved. Here, we have a picture of a climber supported by ropes. In this case, there is another type of forces, that is the tension in the rope. Again, there will be his weight that is acting downwards, the contact force at his feet that is perpendicular to the surface, and the tension in the rope. In dynamics, we treat the object as a point mass, so we can put the forces together. The second type of dynamics question tests your understanding of balanced forces and its relation to Newton's first law of motion. For instance, back to the car going down the slope. The question may state that Newton's first law applies to the motion of the car as it goes down the slope. Explain using ideas about forces the motion of the car. Newton's first law states that every object will continue in a state of rest or uniform motion in a straight line unless a resultant force acts on it to change its state. So if the question states that Newton's first law applies, it means that the car is traveling with constant speed. That is, it is not accelerating. It is in uniform motion in a straight line down the slope. And there is no resultant force. You see, for the car to travel at constant speed, the three forces, weight, resistive forces, and contact forces must add up to be zero. That is, there is no resultant force. Since there is no resultant force, there is no acceleration, and the car continues in its motion at constant speed. At this point, let me highlight a common misconception with regards to objects on wheels. We often think that because friction opposes motion, so the frictional forces at the wheels must be in opposite direction to the car's movement. Actually, when we talk about the total resistive force of the car as a whole, yes, it has to be opposing motion. However, when we zoom in at the frictional force at the wheels, it depends on whether the wheels of the car are driven by the engine or are free rolling. Some cars are designed to have only the front wheels or only the back wheels driven by the engine. This reduces the number of mechanical parts and therefore the weight of the car. This also makes the car more fuel efficient. Now let's zoom in to analyze the direction of frictional forces. For here we have a car where the front wheel is driven by the engine. When the wheels are driven by the engine, it turns clockwise as the car moves forward towards the right. At the point of contact with the floor, the wheel is pushing backwards because of its clockwise direction. Hence, the friction is pointing forward to the right, even though the car is moving forward to the right. So in this case, the friction at the wheel is in the same direction as the car because of the clockwise turning that pushes backwards. How about the frictional forces at the back wheels? If the back wheels are not driven by the engine and are free rolling, then it is a different situation. Imagine if you have a perfectly smooth surface where there is no friction. If you push a block, it will start moving and continue its sliding motion until you exert a force to stop it. In the same way, if you have a round wheel, the wheel will also slide and not turn if there is no friction. So the friction between a rough surface and a car's wheel will cause the wheel to rotate. Hence, for the back wheels that are not driven by the car's engine, it is the friction that opposes the forward motion that causes the wheels to rotate clockwise. So although the back wheels are rotating clockwise like the front wheels, the frictional force in this case is pointing backwards as the car moves forward. In our next lesson, we will learn how to solve the third type of commonly asked examination questions, which test the students on how Newton's second law of motion relates to unbalanced forces.